Ireland, a small island off the coast of mainland Europe, is a wind energy paradise. With high average wind speeds, the wind once powered the entire country for 3 hours straight during a strong storm, and often provided most of the day's power. However, increasing wind power on the grid is not simple, especially with Ireland's small and isolated grid system. Improper management of wind turbines can easily destabilize the grid. From energy storage to grid frequency stabilization, wind energy is a great but challenging resource for building a stable grid. To understand how wind turbines work, we need to take them apart. Inside the turbine is a complex technical system. Turbine blades rotate slowly, about 10 to 20 times per minute, with high torque, which is not enough to generate useful electricity. For a generator to operate efficiently, the generator shaft needs to rotate about 1,800 times per minute. So there needs to be a gearbox between the rotor shaft and the generator shaft. This gearbox is designed in stages. First stage, planetary gears attached directly to the propeller to convert large torque into faster rotation speed, increasing speed by 4 times. Planetary gears have more contact points, helping to share the load between multiple gear teeth. In the second stage, a set of helical gears increases the rotation speed by 6 times. Finally, the third stage quadruples the speed again, reaching the required 1,500 to 1,800 revolutions per minute rotation speed for the generator. Gearboxes weighing 15 tons in wind turbines have become a big worry for power companies. Even though they are designed to last 20 years, they are usually only good for about 7 years before needing major maintenance. Replacing a multi-million-dollar gearbox from a height of 50 meters in strong winds and salty environments is expensive. Maintenance costs can account for nearly 20% of total energy costs. Even so, wind energy is still very economical. Currently, we do not understand the specific cause of gearbox failure, but a common sign of wear is small cracks on the bearing, called white edge cracks. The problem is compounded as wind turbines become larger and more powerful, requiring more gearbox stages to handle the enormous torque from the giant blades. One way to save on maintenance costs is to bypass the gearbox and connect the rotor directly to the generator. However, this requires a special type of generator. To match the grid frequency, the generator needs a large diameter and more magnetic poles, which increases the output frequency by creating more alternating magnetic field per revolution. The largest wind turbine today, Haliade X, has applied direct drive technology. The giant generator, with a diameter of 10 meters, 200 magnetic poles, and a weight of 250 tons, is located directly behind the blades, eliminating the need for gearboxes and reducing maintenance costs. However, using a direct drive system comes with many problems. Permanent magnets require neodymium and dysprosium, and China currently controls 90% of the supply of these rare metals. This leads to fluctuations in material costs and increases the risk and complexity of direct drive wind turbines. Ireland is currently testing this technology at the Galway Wind Park. The blades were so huge that the Latalia railway bridge had to be lowered to transport them from the port. Although it takes many years to evaluate the effectiveness of new technologies, with the increasing size and high cost of wind turbines, direct drive systems are becoming more and more worthwhile. An important challenge is how to match the power from the generators to the grid frequency when the wind speed continuously changes. For generators using permanent magnets, the frequency of the generated current depends on the speed of the shaft. For the generator to provide the American standard frequency of 60 Hz, we need to design a rotor that rotates at 1,800 revolutions per minute, with 4 magnetic poles. Accuracy is very important, as any deviation in frequency can cause problems on the power grid, disrupting the entire system. Grid frequency management is a continuous job. For example, in the UK, grid operators had to monitor a popular TV show to promptly activate hydroelectric stations when many people turned on their kettles to make tea during commercial breaks. This increases the load on the grid, and without a corresponding supply adjustment, the frequency will decrease. Power grids are very sensitive to frequency changes, and even a small change, like 1 Hz, can cause serious problems. During the 2021 freeze in Texas, grid frequency nearly dropped to 59 Hz, pushing the grid to the brink of a full-blown blackout that could last months. Although many people blame the failure of wind turbines squarely, the problem is actually more complex. Images of gas and thermal power plants. Natural gas plants also experienced problems, and Texas, with its isolated grid and high share of wind power, refused to connect to the North American grid to avoid federal regulations. This exacerbates the problem. Wind power cannot regulate grid frequency when it drops, because wind turbines operate out of sync with the grid. Increasing the share of wind energy on the grid requires additional infrastructure to maintain grid stability. To understand the asynchronous problem, we need to review the engineering of wind turbines. The first wind turbines were designed to rotate the generator shaft at precisely 1,800 revolutions per minute. The blades are adjusted so that the blade tips rotate about 7 times faster than the wind speed. If the wind is too strong, the blades will stop rotating to keep a steady speed, but this creates great force and causes fatigue for the transmission system. To overcome this problem, variable speed wind turbines were developed. Instead of relying on a stop rotation mechanism, the blades can change the angle of attack thanks to large bearings, allowing for more proactive speed control. However, this results in variable frequency from the generator. To connect to the grid, power must pass through 2 converters. First convert AC to DC, then DC back to AC at the correct frequency. This is done by rapidly turning electronic switches on and off to create oscillating waves. However, this process takes some energy and eliminates the benefit of wind turbine inertia. Like a train with great inertia, therefore, power grids with many large turbines, such as nuclear power turbines and coal turbines, can handle large loads that appear suddenly without suddenly reducing grid frequency, helping to smooth out sudden increases in power demand and allows grid operators more time to bring new energy sources into operation. Wind turbines have inertia, but due to converters, this inertia is not directly connected to the grid and does not help stabilize the grid. Solar panels have no inertia because they have no moving parts. This is the challenge with renewable energy, increasing its share on the grid without considering the impact on stability. Additional infrastructure is needed to manage this problem, especially as coal power plants begin to close. Ireland has found a creative solution to the problem of inertia. In 2023, they installed the world's largest flywheel, with a 120-ton steel shaft rotating at 3,000 revolutions per minute, at the site of a former coal power plant. The site already has the necessary infrastructure to connect to the grid. The flywheel takes about 20 minutes to reach grid speed, and is kept spinning in a vacuum environment to minimize friction loss. It can instantly supply the required 50 Hz precise frequency to the power grid, providing the necessary inertia to maintain stability. However, to achieve climate goals with increased wind power, Ireland will need 5 more flywheels. These flywheels are not designed for long-term energy storage, but for grid frequency regulation. The final piece of the puzzle is developing long-term energy storage infrastructure. Currently, Ireland has the capacity to store 1 gigawatt-hour of energy, but this is far from enough to meet demand. The Irish government is planning to develop a hydrogen fuel economy for long-term energy storage and export. Under the National Hydrogen Plan, Ireland will become a major European producer of green hydrogen for both domestic and export markets. With abundant freshwater resources from extreme weather, and a favorable geographical location along shipping routes, and the world's 3rd largest aviation hub, Ireland has great potential to develop a hydrogen economy. Hydrogen will be produced from excess wind power through electrolysis, a virtually free energy source. As the market develops, Ireland will exploit its vast offshore wind potential to produce hydrogen, aiming to produce 39 terawatt-hours by 2050. This hydrogen will be used for energy storage, transportation fuel transportation, and industrial heating. Based on this content, can you write the ending for a video made about this content? Ireland's journey in harnessing wind energy does not stop at the installation of turbines, but also includes stable management of grid frequency and effective energy storage. Direct drive technology and solutions, such as flywheels, are already helping Ireland move closer to this goal. Along with the Hydrogen Economic Development Plan, Ireland is preparing for a sustainable energy future, not only for itself, but also for Europe. Let's discover more about Ireland's innovative technologies and ambitious plans to maintain a stable and sustainable electricity grid. This journey not only reflects human creativity and adaptability to challenges, but also opens up new opportunities for a cleaner and greener world.